So we'll record the examples. Okay. So Marcy pulls a backpack on wheels down a 100-meter haul. The 6-Newton force applied at an angle 30 degrees above the horizontal. What work is done by Marcy? So think of it this way. Here is a surface. Here's a backpack. Sometimes you have these backpacks on wheels. And there's a little handle, or like, something extruding from the backpack, and you're pulling on it. And you're pulling on it at a 30-degree angle to the horizontal. So, yeah, I mean, it's just your force in the parallel direction, right? Your parallel force. So your work is just going to be your force, which we know is going to be 6 newtons, but broken down to its horizontal component, so times cosine of 30 degrees, and the distance it travels is 100 meters. So you work all that out. If you use a calculator correctly, you should get 5,196 joules. So pretty simple calculation. Now let's look at Mark. He's actually using more force. Now in this case, let's say he's actually carrying it in his arms, right? So there's no angle whatsoever. Or let's say he's carrying it as a backpack. Regardless, that's pretty heavy, right? It's going to be, a lot of strain on his shoulders, arms, however he's carrying it. But let's calculate his work. So his force is 200. His distance is 100. Now times cosine. Now if we think about it, this is going to be a little confusing. So what do you guys think?
Could it be cos 0?
Could be cos 0. That's kind of interesting. Or is it cosine 90 degrees? It's kind of an interesting scenario here. So the question really is more how much work is he doing on the books, or is he applying to the books? So yes, it's going to create strain for him, right? That's for sure. But he's not pulling on the books, right? He's just carrying the book. So it's kind of an interesting scenario. It's one or the other. It's 0 or 90. Actually, I should do this as let's see if I can do this as a poll. Could I do that? I think you guys established that earlier on. I should realize that's what I was doing. So who thinks this is going to be 90? So this one's an interesting scenario. It's actually going to be 90 degrees. See, if we're 0 degrees, think about it. Here's a backpack on wheels. So you're really then pulling it this way. So of course there would be, because cosine of 0 is 1. So then your work would then just be 200 times 100. So you're basically pulling it in that fashion. 90 degrees means you're actually lifting the book off the ground, and then you're walking with it, right? So then you're actually doing this. So, well, actually, you're not lifting off the ground, because if you would, that would be actually a different scenario.
Wait, but wouldn't W equal 0 then? Because then cos 90 would equal 0.
Right,
and
right.
100 times
So the work he's doing on the books, because he's not actually pulling the books so much, he's just carrying them. So it's kind of an interesting scenario, right? So the work would then be 0 joules. So it's kind of an interesting concept, because now the books are part of his body, right? It's not this separate thing that he's pulling on necessarily. So it's one thing if you have, like, say, a box of books. Let's say you have that, right? You have a box of books, and you're pushing the box, and you're pushing it not at an angle but at 0 degrees. Yeah, that's gonna be a lot of work. That's for sure. Like, you're gonna feel really tired. It's a little different here. Yeah, yes, you will feel tired, but it's almost like the books are part of your body, so you're not really performing any work on the books. So it's kind of, and we'll revisit this down the road this week. So, but that's kind of what's happening. It's more of a conceptual thing than anything else, because you're not. Again, it's not like the books are on the ground and you're pushing a box of books. Yes, if you did that right now, that would be, or like, let's say you're trying to push a bed or a piece of furniture. Totally, that's what's going to happen. So we'll keep moving. So let's clear this. Let's say you carry some books while walking down the stairs. Height 2 meters and length 3 meters. How much work do you do? Okay. So now in this case, you're walking down the stairs.
Mr. Mashne,
Yeah, go ahead.
you get the hypotenuse, and that's your total distance.
No, actually, it's not going to be.
Oh.
Yeah. So again, these are very conceptual, interesting problems. Cool. I could do staircase a little better than that. Okay, so here's the guy, and he's carrying the books. Now, the books obviously have weight to them, right? 200 newtons. And actually, that was kind of what was happening right here as well. So going back to this problem one more time here. What direction is my force? So let's actually revisit this problem one more time. So this person is carrying these books, right? The 200 newtons is actually the weight of the books. And the weight's obviously going. So that's the direction of the force. And your motion, of course, is this way. What angle does that force and motion make? 90 degrees. So that's another way of looking at it too. So coming back to that problem again, force times d times cosine theta. We know our force was 200. The distance travels 100, but the angle between that force and the motion was 90 degrees. So that's one way to think about it again. So here now you have 200. newtons while walking downstairs, height 2 and length 3 meters. So remember, the force is actually going to be going down this way.
Wait, so it doesn't really like just matter the distance because it's going to be kind of zero anyways.
Well, in this case here, you do have a distance that's the same direction.
Oh.
So you do have that you can consider. So the work you would do would be your force, which is, the force, the way of the books, times the distance, which is now 2. And they're going the same angle, force, and motion, so it's actually cosine of 0 degrees. Now, because the force is acting downwards, probably should have done a negative here as well. It's actually negative 400 joules. So yes, you do travel the length, which is 3 meters, but that horizontal motion is perpendicular to the force, so they're going to basically cancel each other out.
Why is that for that example cosine 0 and the other one cosine 90? Aren't they both
it's basically the measured angle between the motion and the force. The force is acting downwards, and your motion was parallel to the surface for Mark. In this case, your force is still acting downwards, right? Because that's the way of the books. Your motion is actually 2 ways. It's this way and down. So what you could do to kind of make it a little easier for yourself is just say, look, I know I'm actually covering some vertical motion. I'm going down 2 meters, and that's the same direction as the force. So that's the work that the books, the work you actually do on the books, because you're actually bringing those books down in the same direction of the force. Because the force, what is the force here again? It's just the weight due to the books, and you're carrying that an elevation, or you're descending down 2 meters. So again, these are more conceptual things we'll hit up and reinforce throughout the week. But I just want to kind of just tell you again, it's really the direction of the force. That's the distance you're looking at. So whatever direction the force is going in, you want to make sure the distance is in that same direction. So that's kind of what we were saying up here again. You want the force in the direction of the distance they travel. So if they're totally perpendicular to each other, like in the case of Mark, the force is pointing down and your distance is going perpendicular, then you're not doing any work. In this case, and the angle between that force and the distance was 0. Here, yes, you do have you are going down, and you're also going horizontally. But again, we're only looking at the direction of the force and the distance being the same direction. And that's why we would use just 2 for that one. Let's try another conceptual one. The suitcase is hanging down from your hand as you ride an escalator. Your hand exerts a force, obviously, because you're trying to hold it. And this force does work. Which of the following is correct? Okay. So again, W is work, not weight, mind you. And again, you could be going up or down the escalator. So let's think about this one again. So your force obviously has to be, well, actually, if you think about it, So your hand exerts a force on the suitcase, and our distance is going up. So we consider work to be positive when you're going up. But if I draw it this way, now your force is still pulling up on the suitcase, but now your distance going, you're descending. So we actually consider work to be negative in this situation here. And part of it also could be kind of like displacement in a way. So, so they are going. So that's why the answer is going to be B for this one. Even though you're pulling up on, we know that for sure. You're pulling up on the suitcase, but the work that that you're exhibiting on the suitcase varies depending on whether you're going up or down. And work by a net force gives an object some acceleration. We know this. Acceleration means the velocity changes. And this is a very interesting equation here, which probably doesn't make too much sense just yet. So we'll come back to that in just a little bit. This is actually a little bit misplaced, to be honest with you. Let's cross it off for now, but I think that's a little bit misplaced. But energy is the ability to do work. And energy due to motion is what we call kinetic energy. So work against force times distance. Force is ma. So there's actually a formula for kinetic energy, and it's right there. It's 1/2 times your mass times velocity squared. Unit's still the same, still joule, it's still scalar. Now this right here, again, it's the energy's ability to do work. So this is going to be your final kinetic energy minus your initial kinetic energy. So let's look at this example here. So you're told that a 0.075 kilogram arrow is fired horizontally. The bowstring exerts a force in the arrow over a distance of 0.9 meters. Okay, so you kind of take it, you pull it back, right? The arrow leaves the bow at 40 meters per second. What average force does the bow apply to the arrow? Okay, so remember, work is force times distance, and work is also going to be your initial or your final kinetic energy minus your initial kinetic energy. So kinetic energy, again, is 1/2 mv squared. So 1/2, your mass is 0.075, and your velocity is 40. Because that's when it leaves. But initially, before you released it, or before you, I guess you pulled it back, you didn't have any velocity whatsoever, right? Because it was at rest. And the force is what we're trying to find here. And the distance it travels is 0.90, right? Because remember, you have it drawn back by 0.9 meters. So right now, the arrow's not moving, right? So it's 0. When you release it, all of a sudden it travels 0.9 meters, and they say that as soon as it leaves the bow, now you have that final velocity. So you want that force that's applied to the arrow, right? From the time you pulled it back to the time it leaves the bow, right? And so if you work all that out, you should get, I believe, 60 on this side. F times 0.90. So F is 66.7 newtons. But the reason why we do this is to really kind of understand that initially, again, so you put it here, you do this. Now we're starting to look at our situation. So we put the arrow on, we pull it back. Now let's call this the initial phase, this right here. Right now it's not moving. Let go. Now it travels 0.9. So in that moment, when it was all the way back till the point it gets back to where it was when it leaves the bow, we're looking at that whole scenario and what force is being applied to the arrow as it leaves. And of course, it traveled 0.9.
Mr. Almashne,
Mhm.
you know the previous equation, W equals 1/2 mv squared final minus.
That is what we have, yes.
So we just did the equation above.
Yeah, it's just I think it was put a little prematurely because you didn't know what kinetic energy was until down here. That's all. But yes, it does apply. Yes. But I just felt it was a little bit premature the way they listed it there. It probably should have gone over here, to be honest with you. So I think now I'm gonna have you guys try some problems. We'll probably do maybe the first few here that are not too bad, but we'll do more computational ones. So I'm just looking at these right now, make sure these are fine. Times 35. It's fine. Okay. Yeah, so let's look at maybe 5 through 10 right now. Okay. So let me clear this. So we'll probably spend about 15 minutes. We'll come back and look at 1, 2, and 3, 4 after the lunch break, but let's do 5, 6, 7, 8, 9, 10. You have the answers right here. And it should be pretty straightforward in terms of what you have to, and have a calculator nearby. Obviously, you want to use a calculator for these problems, but it should be pretty straightforward for those 6 problems. And then, of course, we'll talk about it before we have our break. See if there are any questions. We'll have our break. We'll come back. We'll do 1, 2, 3, 4 around noon or so today. They'll have you guys do more problems 11 through 16. And then we'll talk about 3-2 as well. 3-2 is on potential energy, which is kind of an extension of what we just did right now. But right now we did more kinetic. I'm not sure how far. We'll see how far we go with potential energy today. So yeah, so I'm gonna put you guys in your breakout rooms. So let me clear this. Stop sharing. Stop the